Hi guys. So in the last video, we were able to do a conceptual introduction to Buckingham's Pi method. So now we're at the long-awaited juncture where we get to the really fun application of all we've been looking at so far. So in this video, we're going to solve a problem on Buckingham's Pi method, see the applications of the dimensionless quantities, the pi groups, and how to use the scaling variables to solve the problems. So let's get right into it. The drag force F on a body, so I'm going to be circling the variables so it'll be easier for us. The drag force F on a body in a fluid flow is a function of the body size expressed via a characteristic length L and the fluid velocity V, density rho, and viscosity mu. Perform a dimensional analysis to reduce this to a single functional dependence. Okay, so remember the steps we listed before in handling Buckingham's Pi method. The first thing we're going to do is to list out all the variables we have involved, dependent and independent alike, and their dimensions together. So that's going to be the drag force F. So let's call this F subscript D. So this is the drag force. The dimensions of the drag force is still going to be a force. So that's going to be M LT to the negative 2. Okay, so that's drag force F. Length L, so that's L, is going to have dimensions L. The fluid velocity V, so this is a velocity, so this is going to be length per time. The density rho, this is a density, so this is going to be mass per volume. And the viscosity mu, so this is going to be mass per length per time. So we've done the first step, listing out the necessary variables. So now we need to be able to use the real advantage of Buckingham Pi, which is knowing in advance the number of dimensionless groups. So the first thing we need to deduce is n, which is the total number of variables involved. So counting this, you have 1, the drag force, 2, the length, 3, velocity, 4, density, and 5. 1, 2, 3, 4, 5. So n is equal to 5. Okay? Same goes for m. We need to know the number of independent dimensions we have here. Here we have m. L is here, L is to the negative 3, L is to minus 1. T appears across different forms. So we don't have any repeating combination of these variables across all of these, apart from independently having m, L, and T raised to different powers. So m is going to be equal to 3. So the number of our pi groups, okay, remember that we said is the real good part of Buckingham Pi, is performing n minus m, which is equal to 2. So we're expecting two pi groups when solving this problem. Okay, so that's setting up the introductory part of the Buckingham's Pi method of solving a question. You list the variables, attach the dimensions, count the total variables, count the independent dimensions, and you can estimate the number of pi groups you expect to have. So the next step we have to do is to find the select our repeating variables. Okay, so we said we had 3 types. We had the geometric, so for length. We had the kinematic for time. And we had the dynamic for mass or force. Okay, so this is going to be mass and this is for time. Okay, so how do we do this? For geometric length, we need a quantity that is going to, so let's start scaling variables. Okay, so we need a quantity that expresses length in the simplest, most preferably independent form possible. So that is the length of the characteristic length of the body L. So we've chosen that already. L is one of our scaling variables. We can put a little asterisk to identify that. Okay, so L is one of our scaling variables. So now move over to the kinematic, the kinematic scaling variable, the repeating variable. So we look at which of these quantities indicates the rate of something, how the fluid is changing over time. So we have only one rate here, which is v for velocity. and that's convenient enough. We use that as v. Okay, so that's a scaling variable. And the last one is the mass, the dynamic property. So recall one of our rules was that we can't use the dependent variable as one of them. So we're left with both density and dynamic viscosity. And since we're going for the simpler one, we'll go with density for this, because you usually always go with density for the dynamic quantity. So that's L for geometric, V for kinematic, and rho for dynamic. These are the conventional scaling variables. So anywhere you have any of these are usually what you will go for. If you don't have length and you see diameter, you could go for diameter. Okay, but these are usually the big three of the scaling variables that are to be chosen when solving Buckingham's Pi method. Okay, so these are all we have left to do now is just a little bit of fun algebra. I'll try and keep my entire solution on the same page so we can see what is going on. So remember we said we had two pi groups, and the pi groups are going to be made of the scaling variables and the non-scaling variables individually. Okay, so let's write our pi group. The first pi group is going to be pi 1, and pi 1 is going to be f of d, so that's the first non-scaling variable, times L raised to power a, v raised to power b, rho raised to power c. Pi 2 is going to be, we find the next non-scaling variable, so that's mu, L raised to power a, v raised to power b, rho raised to power c. These are not the same, okay? You can make this a1, b1, c1, and a2, b2, c2, but that may clutter up the screen. But we're solving these differently. These exponents are going to have different values. But so these are what the pi terms are going to look like when we're solving our problems, okay? So we use our scaling variable, we take our scaling variable across each of the non-repeating variables and solve for that. Okay, so now that we have an idea of what our pi terms are going to look like, we can get into solving them with the algebra that is required. Okay, so we know that pi 1 is going to be the same as, so we pick a non-scaling variable, so that's f of d. So we can first of all start with equating this to m raised to power 0, l raised to power 0, t raised to power 0, because remember the whole idea of dimension of Buckingham's pi is to create a dimensionless pi term. Okay, so this is going to be on our left hand side to remind ourselves we want to create a dimensionless pi term, and we're going to start off with pi 1. So the non-scaling here is f of d, so that's f of d, that's the drag force, multiplied by length raised to power a, velocity raised to b, rho raised to c. Okay, so the next thing we can do here is introduce the dimensions respectively. So f of d is the drag force, so that's ml t to the negative 2, multiplied by the length, which is L, multiplied by the velocity, which is the length per time, multiplied by the density, which is the mass per length cube. Okay, but it's important that we remember these are being raised to exponents. So this is to a, this is to b, and this is to c. Okay, so simplifying, expanding this actually is going to give us m l t to the negative 2 dot l to the a dot, so you use the index, the radical for each of these, so it's going to be l to the b, t to the negative b, okay, times l to the b, t to the negative b, multiplied by m raised to power c, l raised to power minus 3c. Okay, for simplification purposes, we can join these together. So that's m dot m to the c, so I'm just trying to bring the terms together, multiplied by l, that's l to the a, that's l to the b, that's l to the minus 3c. Then we look for the time terms, so that's t to the negative 2, that's t to the minus b. Okay, so remember this is the same as m to the 0, l to the 0, t to the 0. So funny enough, simplifying this with the laws of indices, remember m on its own is the same as, so x is the same as x raised to power 1. Okay, so it's important you remember that, so you don't ignore the single radicals when you're performing your simplification. So if we were to reduce this down, it's going to be m raised to power 1 plus c times l raised to power 1 plus a plus b minus 3c multiplied by t raised to power negative 2 minus b. Okay, and there we have it. To ensure these guys are equal, we're going to have to equate the indices. So that means 0 is going to equal 1 plus c, which you can tell c is equal to minus 1. On the other hand, we can do for t first, so we can evaluate b before we get to this long expression that is for l. Okay, so that's, you could start by writing your simultaneous equations first. Okay, so for x to be explicit, so minus 2 minus b equals 0, and 1 plus a plus b minus 3c is also equal to 0. So you could write your simultaneous equations out, so you don't have to keep drawing back to your exponential equations, to your exponents of your dimensional quantities. Okay, so we've got c as minus 1, so to solve for b, something missing. Okay, so that's correct. So minus 2 minus b is equal to 0, meaning that b is going to be negative 2. Okay, so to solve for a, that means a is going to be 3c minus b minus 1. We have to do this carefully. So that's 3c minus b minus 1. So 3 times c is going to be minus 3. Minus b is going to be minus 2. So that's going to be plus 2. And minus 1 is going to be minus 1. So this is going to be minus 4 plus 2. This is going to be negative 2. So a is going to be negative 2. Okay? So if we were to write this out, so that means a is negative 2. B is negative 2. And c is negative 1. What does this mean for us? So remember, this is our expression for our pi term. So that means pi 1 is going to be f of d, l to the a, v to the b, rho to the c, which is the same as f of d times l. So you look for a is negative 2, so l is from negative 2. V is minus 2, so v is from minus 2. And rho raised to power minus 1. If we simplify this, so pi 1 is going to be f of d, which is the drag force, over rho l squared v squared. And we've successfully evaluated our first pi term. Okay, so remember, the steps are simple. You pick a non-scaling variable, iterate it with the other scaling variables, raise them to exponents, expand, and be very careful with the algebra so that you end up with an appropriate simultaneous equation. Okay, so just try and keep our problem on the same page, so you can always refer back to it when, if need be. Okay, so that's all there is. That's the difficult part of Buckingham Pi, the algebraic simplification, trying to keep track of all the exponents and the variables, especially when expanding and dealing with singular terms, and particularly L, that will usually end up being the longest of the bunch. So we said pi 1 is f of d over rho v squared L squared. Okay, this is one half of the problem. So solve for the second dimensionless group. So pi 2 is going to be m to the 0, l to the 0, t to the 0. So you pick the other non-scaling variable, which is mu. So that's mu multiplied by l to the a, v to the b, rho to the c. Recall, these guys are not going to be the same. We're solving for a different set of equations. Okay, so mu is the dynamic viscosity, which is going to have units m, l to the negative 1, t to the negative 1. Okay, you know that L is going to be raised to power A. V is L per time raised to power B, and rho is mass per volume raised to power C. Okay, simplifying this, we're going to have m L to the minus 1, T to the minus 1, that's L to the A, that's L to the B, T to the minus B, M to the C, L to the minus 3C. Okay, to gather like terms together, we're going to have m raised to power, look for the m terms, so that's 2, m to the 1 minus 3C, 1 plus C. Okay, that's for L. So m raised to power 1 plus C times L raised to power. So look for the L terms. So that's 1, 2, 3, 4. So that's L raised to power -1 plus A plus B. And this is the last term, minus 3C. Then the time term. So that's T raised to power. How many terms do we have here? 2 terms. So that's -1 minus B. T raised to power -1 minus B. Okay, so if we were to write out our simultaneous equations, we'll have C plus 1 equals 0, -1 minus B equals 0 as well, and A plus B minus 3C equals 1. Okay, so let's get to simplifying. Now we established C plus 1 is equals 0, so C is going to be -1. Okay, -1 minus B equals 0. So B is going to be -1, making these subject of formula. Then solving for A. So it's A plus B minus 3C. So that means A is going to be, you have to be careful when doing this, 1 minus B plus 3C. It's going to be 1 minus -1 plus 3 into -1. So that is going to be 2 minus 3, which is -1. So A is going to be -1. So we know that A, B, and C are equal to 1, 1, and 1. So if we bring these guys back into the exponents, remember what we'll go for pi 2. Pi 2 is mu LA, okay, mu L to the A, V to the B, rho to the C. So bringing these powers back inside, that means it's going to be mu L to the -1, V to the -1, rho to the -1, which is the same as mu over rho V L. And just like that, we've gotten the second pi term. Okay, so I'm going to have to take this up to make our solution visible at a glance. Okay, so that's all. That is the steps you need to take in order to find your pi groups. Okay, first of all, count your variables to give you n. Identify your independent dimensions, which are usually going to be 3, to give you m. Then that's going to give you n minus m dimensionless groups. Okay, so remember we said pi 2 is mu divided by rho VL. So we've done the complex calculations. All that's left is now to simplify the problem. So how this works is that the pi term that includes the dependence variable, which is f of d, is going to be on one side of the equals to. So what does this mean? Pi 1 is a function of pi 2. Okay, remember where the drag force is a function of the size, length, of the size, velocity, density, and viscosity. So that means the pi term, the dimensionless group that has the dependence variable f of d, is going to take the lead, and everything else is going to be a function. If you had multiple pi terms, then pi 1 was the one that had the dependent variable. It would be a function of pi 2, pi 3, pi 4, etc., etc. Okay? So that's all there is. Let's simplify our solution. So pi 1 is a function of x2 f of d. Pi 1 is a function of pi 2. So that means f of d divided by rho v squared L squared is a function of mu over rho VL. Okay? And that's all there is to it majorly. So if I wanted to isolate f of d and make this the subject of the formula, I could now say that f of d is equal to rho v squared L squared multiplied by a function of mu divided by rho VL. So this is all we've been looking for in the minutes of explaining Buckingham's pi from the conceptual introduction. So remember the steps we took. We listed our variables, listed the dimensions beside each of them, count the number, count the independent dimensions, perform the subtraction to know the number of pi groups you have. So if you look and you see, we had 2 pi groups. This was 1 and this is 2. Okay? And from that, pick your scaling variables for length, time, and mass, which are going to be your independent dimensions m. You need to have the same number. Pick your scaling variables. You can do this beforehand to get an idea of what the pi term is going to look like. And solve for pi 1, solve for pi 2, solve for the necessary pi's. And at the end of the day, you will have your expression. Okay? So some other text. This f is really, it just means that whatever you have is a function of the pi term inside it. So you can usually use any other Greek letter to denote this. So I can say, let's make this bigger. Function of mu over rho VL, and to still have the same effect of the same function. I could use this, I could use k and so on and so forth, just to show that it's a function of the pi terms that are inside it. But essentially, that is all there is to solving dimensional analysis problems using Buckingham's pi method. If you do have any questions, things you don't understand, or questions you have that you would like us to try to solve, do leave them as a post in the community or let us know in the comments. So we'll definitely solve more videos in lectures after this. So look forward to seeing you there. Thanks for watching, and I'll see you in the next video.